Okay, let's get started here. Project number 5 is due on Friday at noon. Final exam is the next main thing that we got after that. That is Wednesday of finals week at 10 a.m. in this room. Are there any questions before we begin? Okay. We're starting a new section today, section 9.6. Just to review a little bit here. Here's the 4 steps of the model building process that we've been talking about. And obviously step 1, data collection and preparation, meaning go out and collect your data, make sure there's no data entry errors. Step 2, reduction of predictive variables, meaning use things like AIC to help narrow down the number of predictive variables to actually examine. Step 3, model refinement and selection. This means now with these predictor variables that you have, you want to look at, well, do I need interactions? Do I need some kind of transformations of them? Do I have any outliers or influential observations that I need to take care of? And then lastly, we need to do what's called model validation. And that's the purpose of section 9.6. Okay. Model validation. In other words, we want to validate that the model will work as we would expect it to. You know, the model is going to work better for our collected data that we've been building our model upon. It's going to work better for that than it probably will work for any other data out there. And so what we like to know is, well, how will it work on maybe a new data set? So we can validate that indeed the model will work just about the same, or will work a lot different, or will perform a lot poorly, which then makes you think, well, should we even use the model? So how can we validate the model? The best approach, or the preferred approach, I should say, is to collect new data. So go out and actually take a new sample. Obviously, there's issues with doing that in terms of, well, it's going to cost more money to take a whole new sample. It's going to take time to get a whole new sample and so on. But if money and time are not an object, then this is the best, definitely the best way to go about doing it. And again, what we'd like to know is, does this model work well now for this new data set? So this is kind of emulating what you would eventually use a model for in the end, to try it on our new data. So what we can do simply is, how about we re-estimate the model for this new data set that we have. So the exact same model that you found, estimate it now with this new data and compare the parameter estimates. In other words, the B's. If the B's don't change a lot, that says your model is going to work reasonably well. If the B's, though, change a lot, then you might be worried. Because now you could reach different conclusions just based upon having an entirely new data set. That's not a good thing to have. You know, think of the idea of the reproducibility of research. You know, if you go out and collect some data, get a model for that data, you hope that that model will be just about the same as if you went out and got another set of data and found a model for that. You want to be able to reproduce your research. So, it's one thing you can do. Second thing is measure the predictive capability of the model based upon the new data set. You can calculate something called a mean square prediction error, or MSPR. I don't know why it's not MSPE. Well, this is the book's notation, so they choose to ignore the E in error and just call it R. Anyway, this is what you do for MSPR. It's very, very similar to MSE, but it is a little different. Sum over all observations in your new data set. So let's say I have n star new observations. Sum over all of them. Take the y's from this new data set. Subtract off what y hat would be for these new observations. These y hats come from using your original model with your original These y hats come from using the b's from your original data set. Okay? So you're not re-estimating a model here. You're using the b's from the original data set and predict then these new observations. Square it, so we get like a squared error. Sum it up, divide by n star, so that you get an average square error. So again, MSE that we have been seeing before, it looks something like this. Obviously, the numerator looks very, very similar, but again, that's for the original data set itself that we're summing over, all the y's, and then computing the y hats for the original data. And notice in the denominator we have n minus p versus n star. Why do you think we don't need to subtract off p for this measure? We're not estimating anything with this new data in terms of the parameters themselves. That's why we don't need to divide by p in order to get an average value. Now, so this is a measure of the prediction error. What we would like is this MSPR to be similar to what MSE is. If it is, great. This model's predicting basically as I would expect in terms of its leftover error. But if MSPR is a lot bigger than MSE, then you need to start worrying that maybe there's something wrong with my original model because it's not predicting as well as it did with the original data set. So something's going on. And you might be thinking, well, maybe I wouldn't even want to use this model then because when I try it on this new data set, it doesn't work that well in comparison to my original data set. And lastly, examine semi-studentized residuals for the new data set, but to check for outliers. But be careful how this is calculated. So over all observations in your new data set, calculate EI star. Take the y from the new data set minus the y hat from the new data set. And again here, you are not re-estimating the model. You're using the original b's from your original model. Divide by the square root of MSE, which makes sense. Okay? And again, you can do that plus or minus 3 from 0 to make a determination if you have an outlier or not. Again, what this helps you then determine is maybe that my model is not predicting certain observations or certain characteristics of my x's, not predicting the corresponding y's as well as I would like. Okay. So again, collecting new data is the preferred method, but costs time, costs money. What's more often done is this, and that is to use a holdout sample. In other words, split your data set, your original data set, into two parts. The first part, let's call it my model building data set, that's where I do steps 2 and 3 of the model building process, meaning I try to find the best model for this model building data set. I don't look at the other data that I had removed from my original data set. That data that I had removed, that's often referred to as a validation data set, and now you try your model out on this new data set. The key is that this validation data set was not used at all to build the model. That needs to be done. They need to be separate. The reason being is because you don't want anything in this validation data set to bias, you could say, your results in the end to validate the model. Some people refer to the model building data set as a training data set, meaning you are training a model and then to come up with the parameter estimates. And then the validation data set is often referred to as a test data set, meaning this is what you are testing the model on. Yes?
When you're doing that, is there any guidelines for how big the two sets or how you select the observations for each set?
Yes, thank you for foreshadowing, something I'm going to talk about. Thank you. That obviously is an important question. And this is also then leads then to a limitation of this approach. If you have a small data set, do you think you can do this approach? Probably not. Because ideally, we want as much information as possible being used with the model building data set. Information meaning observations. Well, of course, then you would like to have as much information as possible used for the validation data set too, so you can validate your model better. So in both cases, you want both model building and validation data sets to be as large as possible. Well, that can't happen in many, many, many instances. Like with the cheese data set that we had. What was the number of observations? It was like about 60? How much? 30? You wouldn't do this approach. It's just too small of a data. You're going to be missing out probably on some important information than with building your model. If you, let's say, took out maybe 10 observations for validation and left 20 as model building. So there are obviously limitations here. And this then shows you that if you can't go out and collect new data, and also if your data set's so small, it wouldn't be good to split the data set, you might not be able to do this step 4. That often does happen. The step 4 of the model building process. So our authors give some recommendations for how many observations to put in model building. A general recommendation that I typically follow that I have seen elsewhere used is using 80% in the model building, 20% in the validation of your entire data set. So if you have 100 observations, 80 in the model building, 20 in the validation. But again, you have to worry about, well, is that 20 really enough to fully validate your model? May not be. So this is not perfect. Now, when you select which observations go in the model building, which observations go in validation, you need to do this in a random manner. So you don't say, oh, these individuals have high school GPAs between 3.5 and 4, so I'm going to put those in my validation data set, and then put all the other individuals in my model building data set. Well, that's not a good approach, because that's going to bias your results likely. So instead, you need to randomly select observations to put in model building and put in validation. I'll show you how to do that shortly. So once you get this validation data set, you basically just treat it like how we did the new data set before in terms of calculate, for example, MSPR. Re-estimate the model. Look for outliers. You treat it the same way. So let's look at the MBA GART data set then. I do have a new data set here. It's from 1998 to 1999, that particular MBA season. Our original data set comes from 92-93. So let's do some calculations here. First thing you do, of course, is read in the 92-93 data, estimate the model, as we've done before. So this is the best model that we found at the end of Chapter 10. Notice how it has a squared MPG term in it, has an MPG age interaction term in it. And then I read in my 98-99 data. So this is available on the course website. And let me actually go on over here to 10 and run some of this code. So total, I have 58 now observations in the validation data set here. And the first thing I need to do is some predictions. I want to find y hats based upon my original model. So I take predict, use the predict function, object equal mod.fit, and again, perhaps I'm overemphasizing this. Notice this mod.fit comes from fitting a model to the 92-93 data. So I want to do these predictions using the 92-93 data B's. But my new data now is this validation data set. So I get my predictions. And there they all are. Okay, this is, we're predicting PPM, if you So next I find MSPR. So I simply say, let's get the ppms out of the 98, 99 data. So this is my y. I subtract off y hat squared divided by 58, and here's my MSPR. Well, what was my original MSE? I go back to my output. So the MSE from the original data, the 92, 93 data, in the output I see residual standard error, 0.08447. So I'm going to copy that, square it so I can get MSE, you get 0.007. So we see, maybe about 50%. This is on page 7, 56.21% increase. So this worries me a little bit here. Maybe my model is not as good as I had thought because my prediction error is like 50% higher. Okay. So also, let's re-estimate the model now, the exact same model, now for the 98, 99 data. So that's what I do here. And then I want to look at these B's here. How do they compare with my original model? So the easiest way to do that is look at relative change. So I take the B's from my new model, subtract off the B's from my original model, divide by the B's from my original model, around the 4 decimal places. And on page 6 I have a nice little table that summarizes all that. And there we go. So we see, for example, the interaction term decreases by 88%. That worries me. That definitely does worry me. And in fact, you could look at now, for example, the interaction term is non-significant. Where before it was. Before I had a p-value of 0.0026. So, this worries me about the reproducibility, again, of my research. One good thing, though, is this. Notice how the signs of all the B's are exactly the same. So it says I still have the same direction of association. So at least I do have that. It makes me feel at least a little bit better. Okay. How about the semi-studentized residuals now? Well, as you would expect, just take your Y's, subtract off their corresponding predicted values from the original model, divide by the square root of MSE that I pulled out. I do a plot in a very similar manner to what we've done in the past. So I'm not going to go over the code. And I plot semi-studentized residuals versus observation number. The red lines are at -3 and +3. Notice that all the observations are pretty much within that boundary. Just one observation, number 30, is definitely outside. So this is a good sign, other than number 30 there. This is a good sign to see when you're validating your model. So we have a mixture of results here. A lot of them are bad in terms of hoping that this model is going to be a good model. And then we have some that are not so bad. This observation number 30, then Eddie Johnson, guard by the name of Eddie Johnson, and he only played in 3 games. Also, his age was 40. So remember some of the results that we had back in Chapter 10, which were, well, we might want to consider limiting our population of inference to regular playing guards. And we define that somewhat subjectively as those guards who play at least in half the games during the season. So this might make you think, well, maybe I should go back to that particular model and try this data set. Try that particular model on a new validation data set that has all NBA guards playing in at least 41 games. I didn't do that here, but that will be one course of action. Instead, what I did was I looked at this age here. In the original data set, the oldest player was 37 years old. So I am actually extrapolating beyond the range of my observed predictor variable values. So because of that, it wouldn't necessarily be appropriate to leave this particular guard and any other guard that's greater than 37 in age in my data set, in the validation data set, that is. And in fact, there happens to be 2 players with greater than 37 years of age, so I remove them both, and I re-estimate my model and recalculate some of these validation measures to see what happens. So first of all, to make sure that I have guards that are less than or equal to 37 years of age, notice how I do this. When I estimate my model using the LM function, I say data equal, here's my original data set, and then I specify less or equal to 37. So just to make sure that this is clear, we've done this before, but I don't think it hurts to talk about this. If I execute this part of my code here, what's going to happen? Get a bunch of trues and falses. And so then when I combine it with the whole data set here that says take the rows that are true, don't use the rows that are false. So just take the players that are less than or equal to 37 years of age. And so here's my estimated model and the corresponding output. I look at the relative change, and on page 10, I have a summary of the results. Note that I usually would not pay attention to the intercept because that's not going to affect your interpretation of a particular predictor variable on the response. But overall here, generally speaking, this looks better than what we had before. Notice the MPG in age now is only negative 25% of a 25% decrease, where before it was 88%. Also, that interaction term is actually marginally significant now. So that's good. The direction of association in terms of the positive and negatives on the B's are the same, just like what we had before. So I am much more satisfied with this than I was previously, although, this is a little, worries me some. And sure, I would like to have some of these be lower, closer to 0, but at least this is a better assessment of my model. And I feel better about the model now than I did before.
Why, for example, didn't you examine all the ranges parameters?
You mean the variables? And perhaps I should do that. I didn't do that. The problem that we found with when you have multiple regression analysis and you have multiple predictor variables is you're not going to be able to really determine the appropriate range for everything because you need to look at everything at the same time.
Not
and
exactly,
so, but you can at least look at them one at a time, and that would be definitely a good approach to do. Unfortunately, I did not do that. What about MSPR? So I go ahead and calculate that. Now it's 0.0088. Compare that to what we had before with the 92-93 data set, 0.007. So now it's a 23% increase, where before we saw 56%. So we see that, again, the model is looking better than what it did before. You got to be careful with this particular measure, too. And that is, the model should predict worse. Generally speaking, it will always predict worse with your validation data set than with your original data set. The reason being is because these B's were, let's say, you can say optimized for your original data. So it should, generally speaking, always do better with the original data than with the new data. So while I like that 23% to be lower, I would say it's kind of borderline if I should be worried or not. And that is somewhat of a subjective judgment. Yes?
Can we examine something like equivalent to R squared or just R squared?
I mean, you could do that in terms of, you go up here and look at R squared there. Well,
I mean,
I'm sorry.
Calculate from the new data set something equivalent.
Okay, I see what you mean. I haven't seen that done before, but I would think that that potentially could be another measure.
Because basically, you look at the change in the MSC, that's okay, but the MSC is really low. It's really low.
Well, but we're looking at relative change.
Yeah.
So we're still looking at relative change.
If it's really low, even small change.
You have to take into the context that the data is measured in. And so, with this PPM, we're already working with stuff that's, using decimal places. There's nothing to the left of the decimal place. So you have to take into the context the scale of the data before you make a judgment like that.
That's what I'm saying. The
So-
PMs are around 0.4, 0.5, and your MSC is
I would look at the number of significant, let's say, 5 significant digits.
1%. The MSC is about 1%, something like that.
Well, I think perhaps I'm wrong, but I think what you're saying is that they're both around about 1%, and so therefore we shouldn't be that worried. But that's not necessarily true. You have to look at the scale that the data is measured in. And because, let's say if I multiplied all the ppms by 10, well, what's going to happen here? Well, that's going to be, generally speaking, I would expect multiplied by 10 too. Does that mean my model's fitting worse? No. It's just I have a different scale for my watts. And so, look at the, first few significant digits to make the judgment. Okay. Well, let's say that I did want to do construct a model of suppose I want to construct a validation data set and a model building data set. So I want to do this data splitting idea. How would I do that? There's a few ways. This is the most prevalent way. You use the uniform probability distribution, which probably most of you have seen before. If you haven't, this is what the uniform probability distribution looks like. So my density function, f of x, has two, and it's dependent upon two parameters. We'll just call them a and b. Is equal to 1 over b minus a for x somewhere between a and b, 0 otherwise. Here's a plot of what the uniform distribution looks like. So I'm plotting it in blue, and we can see that's a pretty kind of boring looking distribution. Once x reaches a, it jumps up to 1 over b minus a, and then once it reaches b in terms of x, it jumps back down to 0. The area underneath, if you call this a curve, is 1, just like with any other probability distribution function. Often the most used case of this distribution is when a is equal to 0, b is equal to 1. So let's say that this is 0. Let's say that this is 1. The nice thing about this distribution is that it has the same height always in this distribution between 0 and 1, is that if I were to look at, let's say, a range of 0.2 to 0.3, and it's not drawn to scale, but hopefully you get the idea. If I look at 0.9 to 1, then the area underneath the curve for both is going to be exactly the same. It's going to be equal to 0.1. So I have always an equal probability being between intervals of the same length. That's the key. So because of that then, if I wanted to, let's say, simulate observations from a uniform, similar to how we did with a normal distribution, I could use a function called RUnif. So I'm going to say U gets RUnif. The first argument is the number of observations, let's say 1,000. And the first parameter in R's syntax is called min. It's called 0. Max is the second parameter, and let's put it at 1. So now I have 1,000 observations in U. And if I say I want to sum if I want to sum u less than 0.8, what do you think I'm going to get? I'm simulating data between 0 and 1 with respect to this distribution. What do you think I'm going to get if I look at all observations that are less than 0.8 and I sum up the number of them?
Should get around 800.
Should get around 800, exactly. So if I say greater than 0.8, you should get about 200. So what this does, it allows you to randomly now generate numbers between 0 and 1, and subject to whatever criteria you put there, like 0.8 or 0.2 or whatever, you can figure out, or you will be able to have observations that, I'm not saying that very well. Let me start over. What you can do is, let's say, assign one of these uniform random numbers to every observation in your data set. And if you want to sample 80% of your observations from the data set, just take the observations that correspond to a u less than 0.8. If you want to sample 20% of your observation, take take the observation that corresponds to u less than 0.2 or greater than 0.8, or in that manner. So with that, then, this allows us to now split our data set. So I'm going to set a C number so I can reproduce my results. I'm going to use then the RUnif function. Sample size is going to be 105 because that's the number of rows in the MBA guard data set. Okay. And what I'm going to do, make sure I'm doing it this way here. Simply, I'm going to look at all observations that would correspond to this unif.split number that are less or equal to 0.8. So just to show you, I get a bunch of trues and falses. And look at just the MBA guard data sets that are in that particular order. So that now the number of rows in my model building data set is 85. So 85 divided by 105, it's about 80%. To get my validation data set, I take unif.split greater than 0.8. So the other observations essentially, put that into my validation data set. And now I have 20 out of 105. That's how you split your data. Once you have your data split, then you can do the same measures that we had just previously done. Any questions? Okay, that concludes this section 9.6 then. Let's go to chapter 11. This will be our last chapter. So we've talked about this semester, problems that can occur with a regression model in terms of, let's say, assumptions are violated, or maybe outliers or influential observations are causing maybe potential problems with our estimation of our model. We've talked about these problems, and we've talked about various solutions to those problems, all within the context of still using least squares estimation for your betas. Now we're going to look at ways that we can, let me back up, if after applying some of these techniques that we learned to try to solve some of these problems, if they don't work and you still have problems, now we're going to have to get away from using least squares estimation, unfortunately. And we're going to have to try something else. And so that's what Chapter 11 talks about. It starts getting you thinking about what other things that could be done in terms of how to estimate these betas that could help solve your problems. Okay, and the first thing that we're going to look at is the situation where we have non-constant error variance. So with our model, again, as we've seen before, get my red pen out. Here's our regression model, and the key is that these epsilons here all have exactly the same variance, which we just symbolically denote by sigma squared. So every epsilon, so epsilon sub I, that's why I have an I here, every single one has exact same variance. That's constant error variance. So our covariance matrix then for the epsilons is just simply an identity matrix with, you can say sigma squared actually on the diagonal elements, or sigma squared times I should say. But what if we had this situation here, where variance of epsilon 1 is now sigma 1 squared. Variance of epsilon 2 is now sigma 2 squared, and so on, so that potentially every single epsilon could have a different variance. Notice that what that also means is every single y has potentially a different variance. Well, what do we do if something like this occurs? Well, in chapters 3 and 6, we talked about particular transformations of y that can help reduce the problem. It won't necessarily completely solve it, but it will at least help reduce the problem so that inference procedures that you do still will work reasonably well. Well, there are cases where those transformations are not going to work very well. And if that were to happen, then you need to change from using least squares estimation to something else, and we're going to talk about something called weighted least squares estimation. So the goal is to get estimates for your betas, just like before, but we're going to use a slightly different technique. And this slightly different technique is going to help us to be able to do inference correctly. Meaning that when I find a confidence interval, let's say for beta 1, or a confidence interval for the expected value of y, and I say it's 95% confidence, I know that indeed, truly, it is just about 95% confidence. If you were to use least squares estimation, and you have non-constant error variance, and you're not able to really solve the problem too well, and you still did this kind of stuff, 95%, it's likely to be incorrect. Might be 90, might be 80, might be 70. That's what happens when assumptions that you make about your model are violated. Okay, so least squares estimation, just to review. Saw this first in chapter 1. We saw it again in chapter 6 and also 5. I want to find these parameter estimates, these statistics, such that my sum of squared errors, the difference between yi and y hat I, summed and squared, is as small as possible. It's a reasonable thing that you want to occur. You want your sum of the squared errors as small as possible. And what one can show then is these parameter estimates, these statistics, come about through this nice little equation. So a vector of my b's is equal to, excuse me, x prime x inverse, x prime y. Okay. The nice thing about these estimates is that they are unbiased, and also they have the minimum variance amongst all unbiased other estimators out there. So what that's saying is that, since we're very, very concerned in statistics about variance, we want variance to be as small as possible. Think about the role that a variance plays in a confidence interval, and what a larger variance would do versus a smaller variance. That's why we want estimators to have as small variance as possible. And so this is why this is so great to use these least squares estimators. But when the constant variance assumption in terms of these epsilons is violated, you no longer have that minimum variance, unfortunately. So what does that mean? Well, it means, for example, like with confidence intervals, they could be wider than what they would be otherwise, which also can mean other issues such as, again, your confidence levels may be incorrect for confidence intervals. So what can be done? Well, we're going to change how we estimate these b's. It's a small change. We're going to find b0 through b sub p minus 1 such that SSE sub w, so weighted least squares, that's why the authors put a w there, such that SSE sub w, which is now the sum of these residuals squared again, but now weighted by something, is as small as possible. So we're still trying to find an SSE that's as small as possible, but we're changing the definition of what SSE is. This W, this weight, is 1 over sigma squared sub I. So in other words, these variances for the epsilons, we just take the inverse of them, put them in there, and minimize SSE. What ends up happening, you can take a look at the derivation in the book if you're interested. You're not responsible for it. B, my vector B, vector of estimates, ends up being, instead of x prime x inverse x prime y, x prime W times x inverse times x prime W times y, where this W is a diagonal matrix with these weights on the diagonal. So, look what happens if sigma sub I squared. What do you think is going to happen if all these sigma squares here were equal to one another?
Cancel out.
They're going to all cancel out. Why? You can go through the math on your own if you're interested. Notice how I have an inverse here? And so if each of these sigma squares were equal to one another, I could factor out a 1 over sigma squared and put an identity matrix in there instead. That 1 over sigma squared, because of that inverse, becomes sigma squared. This right here is going to be sigma squared times I. Yeah, sorry, thank you. 1 over sigma squared times I. And so thus the sigma squares cancel out. So you're left with the least squares estimates. So you can say that this weighted least squares procedure is just a generalization of regular old least squares. That's it. Helps you take into account different variances. For those of you who are going on to Stat 970, you'll be working with this stuff a lot in that particular class. Now, by using these estimators, we still have unbiased estimates, but now we go back to having minimum variance amongst all unbiased estimators, which is what we would like to have. Hopefully all of you, though, are probably saying, well, wait a second, you can't actually do this kind of estimation, because after all, you would need to know what sigma squared is. Sigma squared, or the sigma squared I should say. You would need to know what these are in order to do this weighted least squares, because it's a parameter. Will we ever know what sigma squared I is in the actual application? No. That's like saying you know what your betas are in actual application. If you knew those, why would you be doing this? Why would you be estimating the model in the first place? So, unfortunately, we can't do this exactly. What can we do instead? Here are 5 possible things that you can do. First, perhaps each of these sigma squared i's are just a constant multiple of an overall variance, let's say. If that was the case, then, similar to what I had just shown above here, if all the sigma squareds were equal to one another and how they would fall out, the sigma squares would fall out here, and what you would do is you take your weights then to be this 1 over k sub I, where k sub I is this constant. But again, how do you know what this k sub I is? So, while this is an ideal solution, it's not often one that can be done. Second, suppose for each set of predictive variable values, or each unique set of predictive variable values, I should say, you have multiple observations. So let's say, for example, with the high school and college GPA data set, here's my x. Let's say for x of 3.0, I have, let's say, 10 observations, and we'll call these are m's, m for number of observations at each particular x. Maybe at x equal 3.5, I have 20 observations. Maybe at x equal 4.0, I have 15 observations. So I have multiple observations at each individual x. If that's the case, then what you could do is calculate the regular old sample variance that you learned about in your very first stat course. Calculate that sample variance for each of these. So for 10 observations, I calculate sample variance. 20 observations, I calculate sample variance. And now use these as your sigma squares in your model, in your estimation. Okay? So in other words, you're just simply basically replacing a parameter with this estimate. It should be a fairly good estimate as long as these m's are large enough. Of course, this only works when you have multiple observations at each unique predictive variable. Predictive variables values, let's say. Did we have that with the high school and college GPA data set? No. Did we have that with the MBA GARD data set? No. So, some situations this will work, but in most situations it won't. Here's another thing that can always be done. Do a plot of your residuals versus your predicted variable values. Predicted response variable values, I should say. And if we have non-constant variance, of course, we should see something like that at the top of the page. We have this cone shape, this fanning out, showing that the variability changes as a function of y hat. Or in other words, changes as a function of your predictive variables. Because that's what y hat is, a function of your predictive variables, linear combination. So how about we maybe divide this plot up into maybe 3 to 5 groups. And so I just shown here 4 groups. Where I'm dividing up by different amounts, basically, of variability with respect to y hat. So we can see that this first group has a lot less variability of the residuals than the last group does. Okay? So, motivated by the previous idea in that number 2, what we can do now is find, let's say, the sample variance amongst the y's, or, I'm sorry, find the variance amongst these e's for each of these groups. Just find the variance, and now use these as my weights, or use 1 over these variances as my weights. So you can see again, this is trying to emulate what we had just done for number 2 here. Trying to emulate that same idea. I will show you an example of how to actually implement this shortly. Now, what often, this is now method number 4 out of 5. Now, what often happens is that this variance is actually a function of a predictive variable. And you can see it, the variability increases as a function of the predictive variable, or decreases as a function of the predictive variable. So what you could do is do a plot like this, residual versus x, and you can see again that same kind of pattern that we've seen previously. And what you could do is basically try to estimate the relationship between the squared residuals and x through fitting another regression model. And then try to use this new regression model to predict what the squared residuals would be. Take these predictions for every single observation to find your weights. So 1 over these predicted values. That will be another approach that one could follow. And lastly, one could use what are called generalized linear models. This is a generalization, further generalization to what what weighted least squares, what regular old regression analysis does in Stat 870. Because generalized linear models are discussed in Stat 875 and 971, I will not discuss that in this particular class. But essentially what you do is you say instead of y being having a normal distribution, maybe you could let y have a different distribution that allows you to have different variances. And that's how it works. Okay. Some notes before we get to an example. We've talked about a number of ways that you can estimate the sigma squared I. But in that matrix W that we saw, at least for the estimation, which is a diagonal matrix with 1 over the sigma squared i's in it, you would put then the estimate of the sigma squared I in that matrix. The problem is that with weighted least squares estimation, typically you do not take into account the fact that these are actually estimates. And so there's a source of variability that's not usually taken into account, unfortunately. R squared no longer has the same meaning as it did before because your SSE is different. It has weighted residual squared. The actual covariance matrix then for this these parameter estimates, instead of what we had seen before back in chapter 5 was the first time we saw sigma squared times x prime x inverse for least squares estimates. Now instead we have x prime w x inverse. That's my covariance matrix. And again, on your own, you should think about what happens if I did actually have equal variances throughout this W. Well, you're going to get exactly then the same thing over here. Make sure you can show that to yourself. Okay. Finally, an example. What I decided to do is actually simulate some data that has non-constant variance so that we can evaluate how well multiple estimation procedures work in terms of how do we estimate these weights. And since I'm simulating the data, I know what the correct answer is. And I think this is an excellent way to see how these procedures work and also to see what kind of answer they will provide you in the end. And so this is how I chose to simulate my data. We've talked about simulating data in a regression context a number of times. I just decided to choose x to be a number from 1 to 40 by 0.25. So I'm going to have approximately 160 observations. I'm going to set a C number, and then I'm going to simulate some standard normal data for my epsilons. But I want to make sure that these epsilons actually have non-constant variance. Obviously here, they do have constant variance right now. So what I'm going to do instead is multiply each of the epsilons by a corresponding x. Since these x's are obviously different, that means that these epsilons are all going to be have different variance. In other words, what I'm doing is this, for those of you who've had a mathematical statistics class. If I have, let's say, epsilon distributed normal 0, 1, x times epsilon is distributed what? 0x squared. Let me actually put an I on here. And you can see, since every observation is going to have a different x, every observation is then going to have a different variance for the corresponding epsilon. So that's how I decided to come up with non-constant variance. Once I have that, then I apply stuff that we first learned about in, I think it was chapter 2, maybe chapter 3. I just simply say y gets, I'm going to choose a beta 0 to be 2. I'm going to choose a beta 1 to be 3. Take the 3 times x plus epsilon 2, which contains now this data that has non-constant variance. And put it all into a nice little data frame. using the plot functions we've used before. Here's a plot of my data. Do you think I have non-constant variance? Yes, because we can see how the variability down here is a lot smaller than the variability here with respect to the y-axis. So yes, I do have non-constant variance. Let's do a plot. We can estimate our model using least squares estimation, and then we can plot then the residuals versus y hat. What do you think? Do I have non-constant variance? Yeah, take a look at that. So we have this classic shape that we've seen many times before. Just to make sure I emphasize this, I use just regular old least squares estimation to estimate the model. And just so that I can show you some stuff later on, let's say I want to find a confidence interval at x equals 40. So confidence interval for the expected value y, that is. And so I can use the predict function to do that. I'm sorry, I'm going to actually find a prediction interval. And I'm going to put the results into something called pred. And we'll look at the results later on. Okay. So I have non-constant variance. Let's look at what happens if I were to use one of 3 different ways to implement weighted least squares. And again, remember, we know what the correct result will be in the end. And so we have something to compare to see how good this worked out. Okay, so the first thing I'm going to do is I'm going to break the data up into 5 groups. So this is method number 3 that was first given on page 11.3. I'm going to break the data up into 5 groups based upon my residual versus y hat plot. Estimate a variance for the residuals for each of these 5 groups, and use these then as my weights. So first of all, excuse me, to break the data up into 5 groups, I need to know, well, where would the breakpoints be? So I look at all my y hats. Remember, they would be in mod.fit, $fit.values. This is from the original least squares estimation. And I'm going to calculate the 0.2, 0.4, 0.6, 0.8 quantile. Notice I'm only using 4 quantiles here. Why am I only using 4, not 5? It's going to divide it up into 5 groups. Okay, it only takes 4 to divide it up in 5 groups. I put the results into something called quant5, and here is the breakpoints that I'm going to use to break the data up into 5 groups. This is shown then on page 10 by the red lines. So this is the exact same plot that we saw before, residuals versus y hat. But now I have the 5 groups found. Next, I need to figure out a way that I can tell R that I do have these 5 groups, and then I want you to calculate then the sample variance amongst these residuals for the 5 groups. So I want to find the variance of this, and so on. The way that I can do that is to use the if-else function. We first saw this back in chapter 3. If-else, I'm going to test, is my y hat less than the first element, in other words, the 0.2 quantile of my y hats? If it is, now I'm going to assign this new object called groups a value of 1. If it's not, well, how about we see which ones are in the second group? So I do another if-else, check the second element here for y hat. If y hat's now less than that, I assign a value of 2. Otherwise, I continue going on to the third group, fourth group, fifth group. Okay? So the only new thing here is that I have nested if-else functions there. Then I want to find, once I have that, let me actually show you what ends up happening here. Make sure I have all this in here. So let's see now. So here's my data, and this is the corresponding groups. Why do I see groups 1 and then 2 appear, then groups 3 and so on? Why aren't the 1s, 2s, and 3s, and 4s, and 5s all mixed?
Because of the way that you do it.
Yeah, because of how I simulated my data simply. Okay, notice how the X's are ordered. So now I have these groups. What I need to do is find the variance per group. So I'm going to use a function called tapply. What this allows me to do is apply a particular function, in this case the var function, by groups. So I'm going to say tapply to my residuals. I'm going to apply the variance function by each group. So that when I do this and put that into var.eps, here's the variance for the first group. In other words, S1 squared here is, sorry, I lost my place, 27.5. S2 squared is 149. S5 squared is 839.6. So we can see how the variance obviously does get bigger. Now, an alternative way that's not in the notes to find these 5 different variances that might be more comfortable for you would be to do the following. Form a data frame where you have your residuals and these group numbers in there. And then similar to what we did in Chapter 8 with the aggregate function, we say aggregate formula equal. I want to summarize the E's, the residuals, by groups using the var function, and then my data is in temp, and I get exactly the same results. So that would be just an alternative. That's not in the notes. Also, it has not been uploaded to my course. I don't think it's been uploaded to the course website in terms of this, this extra code there. Okay. So now I have these weights for every single group member. Now I need to use weighted least squares. You can still use the LM function, formula equal y tilde x. Your data is in set 1. And whether or not you have that weight is in set 1 or not, it's not that important. But it needs to be obviously somewhere. I have it actually outside of set 1 in my group.var vector. So all I did was I used the if-else function to assign the different variances. And I say 1 over those variances, and that's how you tell R to do weighted least squares, using the weight argument. I can summarize the fit as well, just like before, and also do predictions, just like before. So that's with 5 groups. I could also do this with 3 groups as well. So that's what's on page 11. Code's exactly the same, except for now I have 3 groups here instead. So that's what the groups look like. I get my estimates and so on. Shortly we will compare all these estimates. Now the last way that we're going to actually estimate these models is to basically take into account how we actually simulated the data. So remember, I am using this. Epsilon is distributed normal 0 xi squared. Make sure that I did put that. Yeah, I did put xi squared here. Sigma squared was 1 for us. So I'm going to take advantage of knowing that information when I estimate my model. In this particular case, notice how this follows page 11.3. I'm going to do a little split screen here. Notice how this follows solution number 1. Each of these variances, these sigma I squares, are just xi squared times a common sigma squared. So what I'm going to do is actually use method number 1 here to estimate the model. This should be the best way to estimate the model because it's using how we actually simulated the data. So what this means then is my weights will be simply 1 over xi squared. So how do I estimate the model? Exactly the same before, where weight now is 1 over x squared. And there's my estimates. I put the results in something called mod.fit3. Now, as we've seen before, if I type names, parentheses, mod.fit, or whatever else you're saving the results from LM from, we get a listing of everything that's in there. One thing that we haven't talked about before is weights. So if you actually want to see the corresponding weights that are used, do mod.fit3 $weights, and you see the weights. So for example, this will be 1 over, let's see, 1 squared. Yeah, 1 over 1 squared. Then the next one will be 1 divided by 1.25 squared, or 0.64, which indeed it is. When you use just regular old least squares estimation, what do you think these weights are going to be? Just 1. And we can also do some prediction here as well. For your own reference, please make sure you read this over. Here's how you can do all those calculations now using matrix algebra. Now finally we'll get us to the summary of the results. And that's really the important thing here. Remove the split. So when I use just regular old least squares estimation, here was B0 and here was B1. Remember, beta 0 was 2, beta 1 was 3. So we can see we are off. But let's look at when I use 5 groups. This is what I call WLS1. When I use 5 groups, look at my B0 and B1. They're a lot better. So using weighted least squares, we can see has improved my estimation. Then when I use 3 groups, better than least squares, but not as good as 5 groups. And that kind of makes some intuitive sense. Because if you're using 5 groups, you have a more finer picture of what these variances are. And then lastly, the actual way that I simulated data, I take that into account, and I get these estimates, 2.04 and 2.98. Very close to what the true values are. I would expect that to happen because I am using the correct way to estimate the model. Well, what about now these prediction intervals? So as I said before, I want to find these prediction intervals when x is equal to 40. I want to find a prediction interval for y. When I use the least squares estimation, look at my bounds, 86 to 165. But for all the other weighted least squares methods, look what they are. They're all very similar. So this shows you the danger that can happen if you use least squares estimates, but you have non-constant error variance. You can get quite different results. We see that illustrated in the intervals themselves. But again, in the big picture, though, each of these are supposed to be 95% intervals, but we can see the least squares differs from all the other ones. And if you were to repeat this process over and over and over again, I doubt that you're going to have 95% of the intervals contain the true value of y. Or even if it did, look at the width. The intervals are probably going to be a lot wider. Okay. Are there any questions about weighted least squares?
Is there some inbuilt way?
Excuse me?
I mean, is there some function, already built functions to this kind?
Well, I mean, essentially the LM function's a built function to do this weighted least squares.
Yeah,
That's
but you still need some sort of function to estimate the weight.
Okay. Yeah, that's the problem. I mean, the weights are subjective. There's multiple ways to do it. I mean, in actual application, they're going to be subjective. You know, how you choose the weights. And what I've done is given you some techniques. I guess I don't ever remember, or at least I have not seen in R, and I don't remember seeing it in SAS before, any, let's say, like in SAS, a proc weighted reg that would automatically make a decision for you. I have never seen something like that before. And I guess that's good because it helps then the person who's doing the data analysis think, you know, how should I choose these weights and which is necessarily a good way to do it or what's a bad way to do it. Okay, section 11.2 then talks about multicollinearity. You know, again, we've seen how that can be a problem. And this just talks about some other ways to handle the multicollinearity problem. I don't think that this is as important as some other stuff in the chapter. And I don't know if I would actually ever use, I never actually used this thing called ridge regression in practice. I think some of the other methods that we've talked about to solve the problem is better. But methods do exist. You're welcome to take a look at it, but you're not responsible for it. And that takes us to section 11.3. And also probably a good place to stop as well. Don't want to start a new section with actually 3 minutes left to go, unless you want me to. Okay, you do want me to? Okay, then that's it for today.